Everybody, if you are fine, we'll be starting our lecture number 4 of computer networks. Now, there are two things that I want to discuss today. One is the network core, in which we have the two fundamental concepts of the circuit switching and packet switching and the basic network types. If we see I'll stop the video so that I can conserve the bandwidth, and I'll use the whiteboard. If you don't understand, just ask the questions. Since there are less participants, you can just use the microphone. Let's see the first basic network types. There are two categories by which we define these network types of network topologies. In first one, we say there are basically three network types, which is the first one as peer-to-peer, the second is client-server, and the third one is applications network. Now, what is this peer-to-peer? Now, if we have, let's say, few of these connected to each other in a certain way, within this network, one node, let's say this node, is communicating with another node, let's say this node, within this. So you allow two computers within the network to connect to each other and to share, file or whatever you want to share with each other. It can be two computers, it can be just a node. What is a node? Any device that can have the processing capabilities, we call them as a node. So there won't be anything centrally controlled. So it's not a central, it doesn't have a central server, or it's not centralized. They can just communicate with each other on their own. The best example of peer-to-peer network that we come across would be the torrents that you presently use. You are using the same network to share files, and the connection is between you and the other person. The second one that we come across would be a client server network. What is a client server network? I would have you as a client on this end and the server on the other end. And what is in between I have? In between I would have a network cloud. How is shown like this. This is a network cloud, or we also call it as IP cloud. On one end, you are connected to it here. Another end here. Now, what is a client-server architecture? This client-server network model usually would have one or more of these servers. And what is the function of the servers? These servers provide services and information to the request, to the person who is requesting. Here, you are the one who is requesting, so the server would request back. Like, for example, you go to google.com. That is a typical client-server network in which you are a client and the servers of Google are providing you the services. What are generally servers? Servers are any devices, typically big, computers, powerful computers, who can provide services like web service, domain name service, internet sharing service, email services, file services, and so on. The worldwide net www that we use is a typical example of a client server network. And this is a centralized system. In this centralized system, we have a central repository in which clients get connected to this center. And the third one is known as application server networks. Application server network, also known as terminal server based networks. It's like thin clients. One of our labs that new labs that have been developed is a thin client based network. And what is that? You when you sit on the terminal, it's a small one. Typically, you might have seen these in the banks. They are known as dumb terminals. Why are they dumb terminals? Like they do not have processing on their own. And what do? Basically, they log into a main storage, main server, and they access files or the softwares over the network. So there are advantages of each of these three types of network. So what we discussed just now was client server, peer-to-peer, and application server based networks. The second type of network that we understand is what we know as the network topologies. What are basically network topologies? Network topology is the layout or pattern that we have. The pattern layout is like you sit in a class. How do you sit in a class? You arrange yourself as rows and columns, and then you sit. This is how we lay down networks, computers within a network as well, which forms network topologies. So simply a layout pattern of interconnections of various nodes, links to form a computer network is a network topology. There are two types of network topologies. The first one that we know is known as physical. The second one that we know is known as logical. Physical and the logical. Let's see. Hmm, can't find that. Well, anyhow, just use physical topologies. It's actually that you see the design of the network based on layout of computers. Like you put a computer in your home connected with a laptop, then with a printer, or you see your lab. How do you do this topologies? There's a specific subject that deals with this, which is known as the graph theory, which in which you give the distances between the nodes, the physical interconnections, and so on. Now, what are these topologies? The main physical topologies that we come across is point-to-point, bus, star, ring, tree, mesh, and hybrid. We'll take these seven. You might have studied this in data communication, so I will roughly go, revise the two physical as well as logical topologies. Let's first take the point-to-point topology. Point-to-point is a simplest topology of the two. What do we see in point-to-point? We have a computer here. This is, let's say, your computer, and a computer here that is your friend's computer. Now you want to transfer some files between the two or simply play a game together. So you will have a wire connecting the two devices like this. This is the simplest of the topology, which is the point-to-point topology, or we also know this as P, P to P, P to P, point-to-point topology. This is a basic, conventional telephony that you have come across. The telephone connection that you get is a point-to-point connection. The link that we get to our computer center from BSNL is a fiber link directly laid down from the router of BSNL to the router of computer center in NIT. That is basically a point-to-point connection. There can be a dedicated one like this one, which is always there, or there can be a circuit switched network as well, in which it can be changed, dynamically dropped when it's not needed. It's not permanent or dedicated. The second one that we come across is a bus topology. What what is a bus topology? We have a different pattern of nodes laid across, and there is a link, a main link in between. Each of the node is connected to the main link like this. Now you all know this, simple to understand, that a main wire, or what we call as cable, is spread across and there are different computers connected to it. But certain points that I would like to add here is at the two ends of this topology, there are two things. One and one is here. This is actually on the wire itself, here like this. So this main cable would have a terminator at 2 points, at the two ends. What is a terminator? Well, you might have seen the movie in which the Terminator, destroys the things around. Or likewise, the terminator here is to destroy the signal. So if there is a signal which is passing through this, it will ensure, if this is the signal, which is passing through the network here, it will ensure that at this point where I have marked a tick, the signal will not bounce back within the cable. Means it will dampen, it will absorb the signal such that when nodes are communicating, this signal doesn't keep on moving inside it again and again and again and again. This is what we know as a terminator. It prevents signal from bouncing back. Basically what it has a very high impedance which doesn't let the signal to bounce back. The signal can travel in both the directions. Okay. It actually signal is sent to all the nodes within the network. If, for example, here we have A, it wants to send to B here. All the nodes in between, that is C, D, and E, would also receive this signal. This is what we know as a broadcast signal. But then we have some checking mechanisms wherein we compare the MAC addresses, IP addresses, so on, and only B would be able to receive the signal, which we'll discuss in the future classes. Okay, the good thing is that it's cheaper because one single wire is laid down. It's inexpensive. But on the other hand, there is a disadvantage that it is a single point of failure. What is single point of failure? It means if this wire is down, then the central wire, then what would happen? The whole of the network would get down. This is the problem with this. There are two types which you call single point of failure. There are two types of these buses. One is known as the linear bus. The second one is known as a distributed bus. This, what I have shown here, is a linear bus, a straight line and nodes connected to it directly on that straight line. So a common transmission medium having exactly 2 points. I will mark the 2 points here with the blue color. This is 1 and this is 2. And this is 2. So these 2 points, these two endpoints in a straight line denote a linear bus. This is also known as a backbone in terminology, network terminology. You may also hear a term like trunk. And all the data has to be transmitted through this main backbone or this main trunk. Okay. Now, at the 2 points 1 and 2, I mentioned there would be a terminator. And what is terminator? It has, properties of impedance, characteristics impedance. We have a surge impedance in which it absorbs the energy and doesn't let the signal reflect back, so that it does not keep on propagating again and again within the same middle bus. This is also known as electrical termination. The second type of bus that we come across is known as a distributed bus. And what is a distributed bus? I would have another connection here like this. This would be connected to the main bus and it will have some more nodes connected to it, like this one, this one, this one, and this one. So in other words, I would have a third point here, which I would say number 3, the third endpoint. This is known as a distributed bus. Distributed bus would have more than one endpoint, or I would say, in other words, the main bus would have branches in it. Any questions till now? Anybody? Right. I'll move a bit faster because these topologies are actually basic ones, and you should by now know these. You might have already studied this. I'll move to the third one, which is known as a star topology. Why we call it a star? Because we have a central hub, and to this hub are different nodes connected to it. And the node can be a printer, a server, a desktop, a laptop, and so on. In this manner, which resembles to a star. The network is formed by a central host. You call that as a central hub, which is denoted by blue colored this rectangle. And to it are different nodes connected to it. Each node here forms a point-to-point connection. Like I just now mentioned, the first one, point-to-point. So this hub in the center and the node here, let's say this node number 1, this forms a point-to-point connection between an node, or I would say simply hub rather than node. I would term it as H. So between 1 and H, there is one point-to-point connection, between 2 and H, between 3 and H, between 4 and H, and so on. So if we combine all these point-to-point networks with central hub, we form a star topology. All traffic, let's say you have to communicate the traffic from 1 to 4. All the traffic has to pass through this central hub onto the node 4. or I would say all the traffic traverses through the central hub. The hub also is known as the one which acts as a signal booster, or what we have as a repeater. We'll come to these, networking components in a little while, in which we'll come to this repeater. That is basically, a signal regenerator. The star topology is known as one of the easiest or simple topologies to make. Place a node and start working. In your hostels, you might have created your own star topologies. A few would have bought a hub and others have connected to it, and you would have started playing games like Need for Speed and Counter-Strike and so on. That is what we have as a star topology. The advantage is this simplicity of adding nodes. You have a 32-bit hub. You keep on simply adding 32 of nodes to it. But again, the same disadvantage that we saw in bus would be a central point of failure. And in this case, we have the hub being the central point of failure. If hub is down, if this is down, obviously the whole of the network is disintegrated and there won't be any transmission. Okay, there are some types of stars, like for example, we have an extended star. What is an extended star? You have one star here. You get connected to another star here, like this one. Two stars would get connected to each other like this. This is what we have as an extended star. This would have uh, a number of central nodes, not just a single node. If one of this star fails, other can still work. And it's like, peripheral nodes, what we also known as spoke nodes. It would be connected to a different hub. This would be basically an extended star. Another type that we come across is known as a, daisy chained star, or what we call as a distributed star. Means stars connected in a linear fashion. Like I would have here a third star. Right, if this is a third star, this linearly connected in a daisy fashion is known as a distributed star. And the fourth one that we come across is a ring topology. What is a ring topology? Easy to understand. We have nodes formed across, placed in a form of a ring, connected to each other, forming a ring fashion, or simply a circular fashion in which data travels around the ring. Keep in mind that data travels in one direction. Like for example, if travels, it would travel from A to C like this. And if I has to travel from A to D here, it will travel like this. Well, then you would say that why not the shortest distance? Nowadays, we have ring structures in which we have multiple, layers, different topologies which look for a better transmission through the shortest path. We'll see that as well. In this case, just remember that data would travel in a ring in one direction. And what is each device? Let's say this device is X between A and C. This X acts as a repeater or, you know, passing on the signal from A to C. It helps in the transmission of signal, or it helps in connecting A and C. Means this X would have a receiver as well as a transmitter in which it receives the signal from A and then transmits to the next one, that is C. The R structure that we have in the college campus is mesh, this ring-based fibers. Then you might have studied about mesh network. Mesh network, one of the costliest networks, because you expect each of the node connecting with every other node. So links between all the nodes have to be there, like this one. What I have drawn just now, this is known as a fully connected mesh or a fully meshed network. And if there are like 1, 2, 3, 4, 5, there are 5 nodes. To know these, like how many communicating links we need, we use an approximation by Reed's law, which follows actually Metcalfe's law, in which if n are the number of participants or the nodes that we have, the number of links that we have or the number of possible connections between these are n into n minus 1 divided by 2. So here we will have 1, 2, 3, 4, 5 nodes. So we have 5 for the 20 divided by 2. That would be approximately 10 links between these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. We'll have these many possible connections or links. Now, obviously, having such a network is very costly, and it would be very, messy. Like I would say messy in the sense that how many wires would move around. Typical, I mean, it's a costly one, then why would we use? Typically, banks would use such a network in which they would make sure or they would ensure that there is a redundancy always. What is redundancy? It means that if I have a node here and one of the link fails here, I still have 3 more links. Even one is down, I still have 2 more links. So likewise, I have a good redundancy. But this doesn't always help. So rather than having such a mesh, what we do not necessarily have a fully connected mesh. We can have a partially connected mesh, like this one. There isn't connection between each one. Why? Because fully was very costly and very complex. Actually, practically, if you have 100 ones, so it would be impossible to implement with so many connections laid around. So we would have a partially connected mesh. What is a partially connected mesh? In which you have a redundancy. Like for example, in the same case, if this link is down, I still have 2 more links through which I can get the data. So there is redundancy there. There is some, failure mechanism provided. If one of the links is there, I would have a backup mechanism. It's not that expensive and it won't be that complex as compared to a fully connected mesh. The next one that we have is a tree topology, typically like you have seen in data structures, how it looks like a tree. You have nodes here. You have nodes here. Then you have nodes. I mentioned what nodes are. Nodes are basically any, system having processor, having memory. They can do transmission and so on. They are known as nodes. It can be a printer, it can be a computer, laptop, server, and so on. Like this one, it's a tree topology. This is also known as a hierarchy network. Why? Because we have levels. This one here with the blue one, this is a central root node, or this will say the top of the hierarchy, top level of the hierarchy, if you see it upside down. If this one fails, you still have a small network here working as well as a small network working here if this one is down. So it doesn't have that way centralized, but it is centralized in case you want to send from A to C, you cannot, but A to B, you can do the transmission. In order to define a tree network, how many levels do we require? Yes, anybody can write in the chat. I'll say the questions once again. I'll say the question once again. In order to have a physical hierarchical topology of tree, at least how many levels are required? Good, at least three. Why three? Why not two? If I mention this two here, it would be a point-to-point network. I would necessarily require a third level for it to form a tree type of network. You can have with a branching factor of 1, then it would be a linear topology 101. Then we have more than one, then only we can have a possibility of having a tree with a root node. Okay. Then also we have hybrid types of networks. What are hybrid types of networks? Hybrid type of network is, for example, a mixture of the two in which I have a bus on one end, okay, and this bus connects to a star. So mixture of any two networks would constitute what we know as a hybrid network. This is an example of a hybrid network. Any questions? This is what we just now discussed was a physical topology. Next, what we'll discuss is a logical topology. What is a logical topology? Logical topology is, in a way, how the signal acts, how the signal is passed within the media, how, what connections have you used. So basically how data passes from one device to another device without regards to the physical, without actually regard to the physical layout, whether it's a star, whether it's a bus, is known as logical topology. For example, a twisted pair Ethernet is a logical bus topology, which works in a star topology layout. We'll come to this, star Ethernet versus the ring topology as well. Normally, the logical topologies that will come across are associated with the MAC methods, that is the media access control methods. We'll see that in layer 2 when we are discussing this. Some books would term this as signal topology as well. So logical topology or a signal topology, they are interchangeable. Okay. So keep in mind, we are not talking about the physical layout of wires, physical location of it, physical location of the devices. We are actually talking about electrical signal that passes through it, how data flows through it, and so on. Now, there can be other types of networks as well. We saw first one, the peer-to-peer. The second one, we saw the topologies. The third one can explain the topologies as centralized and decentralized. I would suggest you go through it. I discussed like star is a centralized net topology, or bus is a centralized topology, whereas ring is a decentralized topology, or a mesh is also a decentralized topology. You can go ahead and study the two. Okay, the next part of it I will give you as an assignment. I have networking components and devices. I want you to go through it. In the Google class, I'll give the list that is to be done, that you can just write and send it to me. That would revise these basic networking topologies. And also we can have some basic networking types. That will be your assignment number one. Next thing, that is the important thing that we have to discuss today. I mean, now on we'll be discussing some good things. Till now we are discussing some basic things regarding these topologies and the introduction part. I'll move to network core. There are two fundamental approaches of packet of sending messages. The first one that we have, let me see if I can write some text. Mm-mm. Do we have some way writing text within this? It will be easier for me. Which icon I have to press for typing? I I tried. Yes, yes. Okay, good. So we are now taking. I want everybody to understand this part. If you're sleeping till now, no issues. Just wake up. Now we are discussing network core. And the network core is of two types. Either we discuss this as circuit switching, and the second one that we have is known as packet switching. Circuit switching and packet switching. Now let's take the first one. The first one that we have across is circuit switching. In the circuit switch network, if you make a network, let's say we have a network between these. In this circuit switch network, that is the first one. If we are doing transmission between, in this case, the two devices, that is A and B, the resources needed along a path. What are the resources? That is the buffers, the bandwidth, and so on. The resources along the path that is between A and B are reserved. Keep this term in your mind. Reserved resources. Reserved resources for circuit switch. Whereas we have packet switching in which resources are not reserved. Try to understand what we mean by reserved and not reserved. Let's say, let's take first an example, a simple example. you are going to a restaurant to have a meal. Now, there can be two ways in which you go to the restaurant. You first call them and tell them, I'll be coming at 2 p.m. for lunch. Please reserve a table for me. Or you just decide that I'll go at 2 p.m. You take a car and reach the place where you have to have the lunch. Now, what happens in this case? In the first case, when you have called the restaurant guy would have placed a reserved sign on your table so that at 2 p.m. when you reach, you'll go directly to the place. You'll tell them, "Hi, my name is this." They'll say, "Yes, please come," and they will provide you the seat. And in the second case, wherein you have not called, you have not made your reservation, you can go there and tell them that I want to have a lunch there. They would say there can be two scenarios. If there is a place to sit, they would simply say, come and sit. And if there is not a place to sit, they will say, sir, please wait. Once we have, a place empty, you will be given a place. Okay. So in first case in which you reserved it, it is a circuit switching network wherein you have a guarantee that you would get this much of bandwidth and you will be connected to B through this network. And in second case, wherein you did not have a reservation, you you made demands for each resources. That's resources on demand. You can get the resources from A to B, or you might have to wait for some time. That is queue for access to the link. This is a simple example of analogy of the restaurant. Telephone networks are example of typically switched networks. Like you dial a connection when you are connected with the other person. In the sense that your network or your link between you and your friend would not be broken. You will be continuously connected with the other person. But what you had to do, you had to dial the other person. That is like you had to establish a connection between you and your friend. And this dialing of a network, like you made a phone to your friend, this constitutes a circuit in telephony once the link is established. It will have all these intermediate nodes like I have shown here, 1, 2, 3, and so on. But once a connection between A and B is established, others would not disturb you. You would have a continuous connection with it. And if the telephone company says that your telephone, you will have a bandwidth of, let's say, 64 kbps for this voice call, it will continuously be this much for you. It cannot be lower than that. Means you would have a reserved bandwidth, what we call as a constant transmission rate. Constant transmission rate. Again, this is associated with circuit switching. So after the connection has been established, your resources were reserved, you will get a constant transmission reserve. This is also a, when I say constant transmission rate, I'll use another term here, which is guaranteed constant rate. Again associated with circuit switching. Okay. Compared to this, we can have internet as a packet switching network. What we use, how I am communicating with you. It's basically a packet switch network in which I dial through this WebEx to you. I do not have any reserved guarantees like you will have a constant transmission rate of this much. No, it will depend upon, let's say, at this instant of time, I might have 100, kbps, and at some instant of time, I might get 1 mbps. That's why internet service is known as best effort service. Best effort service. Okay. How to explain this best effort service? Uh, let's say, mhm, I have here uh, Naveed. Okay, Naveed, are you listening?
Yes, sir.
Okay, Naveed, tell
Yes.
me two of your names of two of your friends,
Murtaza Ankur.
Murtuza and Ankur. All right. Who do you trust more?
No,
No, for my example, you need to trust one of them.
sir, Murtaza.
Okay, fine. Thank you. Now let's take the situation in which Naveed has two friends. One is Murtaza, another is Ankur. Now, if Naveed gives 1,000 rupees to Murtaza, he knows that Murtaza would give me back. Say Murtaza would tell him, okay, after 1 week, I will pass you back. And after 1 week, Murtaza gave 1,000 rupees back to Naveed. Okay. Now compare to this, well, this in this case, it's like a guarantee that you get that I paid this 1,000 rupees, I will get this back. Compared to this, Naveed gave 1,000 rupees to Ankur. Now Ankur is best effort service, in which he says, Naveed, I will try my best to give it back, but I do not promise that I will give you back, and I do not promise that I will give you back within 1 week, but I'll try my best. So this is what we have as an internet service or best effort service. That I do not guarantee that I will give you 1 Mbps altogether always. No, but I will try my best to give you 1 Mbps. It can go to 500 kbps. It can go to 100 kbps. That we have as best effort service. Okay, this is a part of packet switching that we have. Packets go into the network without actually reserving any bandwidth. If what happens then if there is a congestion in packet switch network? That is what we discussed in the previous class, that each device would have a buffer. The packet would be made within that buffer, and that buffer would constitute some delays. The term that we used in waiting to get transmitted, that delay is known as, anybody? Yes? Any participant in the chat, or you can use your microphone. What did we call that delay? Nobody? Let me make an offer. +1. Nobody? It's simple. You are made to wait in a queue, which is in the buffer. And it's a queue delay. Anyhow. Okay. Next thing is when we have a circuit switching network, like the one which we said just now, telephone. Okay. Then does that mean that telephone network would have one connection from BSNL Srinagar to NIT, or let's say I have my phone. It has a one line from me to them. It would have a link, let's say my landline, but then this link can be shared by others as well. So in that case, how do we ensure that the link in circuit switching is there, but it is shared as well as it is reserved? For that, we have concept of what we know as multiplexing. So we would have multiplexing in circuit switched networks. Either it can be FDM or TDM. Now, what is frequency division multiplexing, time division multiplexing? Might have studied again in datacom, but I'll still. Have you studied it in datacom, Ramanand? Have you studied? Okay, then I will just revise this a bit so that it is refreshed. What is FDM and TDM? FDM is frequency division multiplexing, in which, let's say I have this link. Okay, within this link, what I do is I divide the frequencies in such a way that I get different channels. Like one link, now I would have a number of people using the same link, 1, 2, 3, 4. So in a way, I would divide, let's say if I had a 16 kilohertz link here in total, now each one here would get divided by 4, that is 4 kilohertz. Now how do you say that I have reserved? My link, that is number 1, would always be 4 kilohertz, that is reserved for me. It will not go below 4 kilohertz. But within the same time, this link can be used by others as well, like 2, 3, and 4. This is what we have multiplexing here. This is how others can also use this link in circuit switched networks. But the disadvantage that we'll have here, advantage was multiplexing. Advantage was 4 people use this one link at one time. The disadvantage is that I have a carrying capacity of 16 kilohertz total within this link, but I am getting 4 because of sharing. But this 4 is guaranteed transmission. I would get this much of bandwidth, this much of frequency for transmission. What we do is frequency multiplication. We like for example, FM that you hear. What do you do? You share microwave frequency spectrum. Okay. Compared to this, the second thing that you might have heard about is time division multiplexing. The similar link that we have here, I will draw the link here. Now, in this case, what we do is rather than dividing it, horizontally, I would divide it vertically. And each one, like we have 4 connections here, each one would get one slot. What does this remind you of? Anybody? Have I shown something like this before? Ramanand, who else is there? Gantt chart, exactly. Yes, Naveed has replied there as well. Yes. And typically, yes, this is a Gantt chart, but this is the Gantt chart of what? Yes, marine processes. What is it? Gantt chart of what? Which scheduling algorithm? It looks like. What? No, no, doesn't look like first come, first serve. Doesn't look like it. It looks to me like round robin. 1, 2, 3, 4, 1, 2, 3, 4. And yeah, that reminds me, I have brought your papers back home, so I'll be starting. Hopefully by today, I'll start marking them. Okay. Yes. No. Okay. Now, what happens here is that if I have a link and I use TDM, that is time division multiplexing, I divide the network here into a frame, and each frame would have a certain number of time slots, and each time slot is given to an individual node. Like I am number one and I'm transmitting this time, I would have this time slot to transmit. Next I will wait, I'll get this transmit, and next so on. That is how I would be transmitting. But this would be so fast that I wouldn't realize that there would be like, I would have to wait. It would be very small wait until I get back the link. So when a connection is established, means I from A to B would have first established a connection. I would have a link dedicated to me. And within this link, then I would follow time division multiplexing in which I will get time slots. How is it advantageous than the previous one? If the link carrying capacity was 16 kilohertz, during this particular time slot, I would get the whole of this 16 kilohertz bandwidth during this particular time. And I'll get these periodically back, these. I would have this time slot dedicated to me. So what is resource reservation here? That time slot has been reserved to me. And you can check in your book as well the transmission rate. The transmission rate of a circuit in TDM is frame rate times the number of bits within a slot. Or in other words, if I'll just type it here, if the link transmits at 8,000 frames per second and each slot consists of 8 bits, then I would have transmission rate as 64 kbps for this one. Okay, this was about circuit switching. Any question till now? No? I'll continue. I'll finish this packet switching today. Next thing is packet switching. Now, what is basically here packet switching? I have this source that is me that is transmitting to my friend that is this one here. So let this be A and let this be B. And I have intermediate nodes here like these, let's say these are routers, and I would have switches in between, and I would connect them using some links. Packet switching, we use basically packet switching. Internet uses packet switching. What is packet switching? We have a message that is to be delivered. Let's say a music file, and my music file is this, which is of 10 MBs. We do in packet switching is that the source breaks this 10 MBs into smaller packets, a number of these small packets. Okay. Why? Because if we start transmitting this 10 Mbps all together, it would take up all the resources with the internet. I'll come to that when what the difference between packet switching and message passing. We'll term that as message. Here, I had this file which is in blue, a music file. I need to transmit this to my friend, that is B. I broke this music file into number of smaller packets to transmit. Fine. Now, these packets travel through communication links that are given in green and through the nodes like routers. Let's say this is our router R1. This is our router R2. There are intermediate switches here, S1, S2, and so on. Now, this packet, when packet 1 leaves from A1 to R1 using this link, okay, when it gets the chance to use this link, it uses the full transmission rate that is available. I'll write this here. It uses the full transmission rate. First thing, the message, I repeat, message was broken into packets. Packets travel along these intermediate switches, networking devices, routers, and the communication links. And then packets are transmitted at a full transmission rate of the link. Means if it's giving you 16 kbps, you will get all of it for you, because you will be the one who would be using this at that particular instant of time. Okay. Now that comes to another point in which, you know, you broke the message, you send it through this full transmission rate. If now the difference here would be, if your link is available, you would get a chance. If the link is not available, you would have to wait. Wait where? For example, you are in R1. R1 is already transmitting some packets from R1 to S1. You are waiting here, and it would have its own buffer. Let's say this is the buffer here, buffer of router 1. Likewise, it can happen to other networking nodes as well. Now, what is this delay here? Most of these switches here would introduce a delay which is known as store and forward delay. Store and forward delay. What it means? Store and forward means that if you've started sending packet number 1 here, this one, R1, and if you actually see what this packet is, it would be a stream of zeros and ones, a long stream of zeros and ones. The store and forward means that when R1 receives the first bit here, it would have to wait for the entire packet till it reaches the last bit. And then it will start transmitting this packet to the next one. So this one would first come here and get stored within R1. Once the complete packet here, the one which I have drawn as a rectangle, is received within this R1, then only it starts transmitting to S1 here. This delay is known as store and forward delay. How much would that store and forward delay be? Store and forward delay would be directly proportional to, what do you think? How big the packet is. That is, I'll say, let's say L, length in bits. I'll just write here length of packet, length of packet that we are transmitting. So bigger the packet, the more store and forward delays we have. You used in your previous class a ping that was of 32 bytes. Compare this with 65,500 bytes. The packet may have a biggest one that we have. Obviously, it would be more. As an example, or simply, if a packet consists of L bits, write down here, packet of L bits, and we have an outbound link of R bits per second, then what we have store and forward delay, or as store and forward delay at the switch as L by R seconds. All right. Any question? Again, another thing that we have to see that each router, let's say I'm taking this router, not erased all of it. Let's say this is a router that we have. I'll term this as R. And this router would have different links connected to it. Let's say one link, second, third, and fourth. Like you are here A, and then B. So this is one node and this is another node. So when packet was sent from A, packet reached here. The first delay it found was store and forward delay. Then once it has processed, router found out that this packet has to be pumped from this end to this end, or from this link, this is known as incoming link, this link which is outgoing link here. I'll name it input 1 and input 2. In this case, if this link is already busy, I'm talking about this link here where I have put a tick mark, then it would have, a router would have a buffer here which would store this packet temporarily here. Trying to move this packet. Let me draw. So this packet would be temporarily stored here. This is known as an output buffer. What is an output buffer? A small temporary storage in which you keep the packet until the transmission line is empty. So if an arriving packet needs to be transmitted across the link, it finds this link, the one which has a tick, busy with transmission. So this packet has to wait in an output buffer. So I'll term this as output buffer. This is again a delay in which a packet has to wait in a queue. Constitutes queuing delays. How much would this be? We discussed in our last class also, depending upon the network congestion, depending upon how many packets have been transmitted over the link, or how much it would have to wait. Again, this is a temporary storage. It's a finite space. Buffer is full. The incoming packet would get dropped, which I had shown you previously with a mark like this. If buffer is full here, no capacity to take, we will have packet drops given here. Packet drop, you can call it packet loss as well. It's like you arrived at the restaurant, you didn't have a reservation. So what did you do? You told the receptionist that I need a table. He said, sorry, we have already table occupied. And there are some people which are already waiting as well. Means within the queue there. Some are being served, some are waiting to be served, some are in the queue. Now you do not have even the place to sit in there in the queue. So what do? You just leave. That is what we have here as a packet drop. Okay. Any question till now? No. Okay, last part for today. I know I'm prolonging, but let me take the last part of it. Since you are all in a cozy place, so at your home, so we can continue. The last part of our today's lecture about packet switching, in which I will draw a network with, let's say, a couple of routers. Okay, I would have some nodes here. Let's say A, B, C. All are connected to each other through the links. Okay. Now I have here A, I have here B, and I have here C. The transmission is between A to C and B to C. I have a link capacity of, let me first say, these are the two routers. This is R1 and this is R2. Now I have the link capacity between A and R1 as 10 Mbps and between B and R2 as 2 Mbps. Okay. Between R1 and R2, I have a link capacity of, let's say, 5 MB. Now, when A starts to transmit, okay, these are the packets denoted by red color. These are the packets which A starts to transmit. If only A is transmitting, A would transmit at the rate of, let's say, 10 Mbps, then there would be a queue within the router R. Let's say this is the queue or the buffer that I have within R. And then it would pass on at the rate of, let's say, 5. Now let me change this 5. I'll change this to, let's say, 10 Mbps. Let me have this as, let me just remove this. So I will have these red ones moving across R1 and R2 at the rate of 10 Mbps. No issue with it, right? But if now at the same time we have B also starting to transmit the packets, which is denoted by these pink packets. Now what would happen here? I am having input of 10 plus 2, 12 Mbps and an output of 10 Mbps only. Both A and B start to transmit using their full capacity of 10 and 2 Mbps each. Obviously, there would be some packets which needs to be stored within the queue. Based on the queuing mechanism, you can have varying ones. Like say there are some packets of, B which have been kept, and there are some packets of A which have been kept within it, within the queue. And then how would R1 transmit this data to R2? R1 would transmit based on some queuing mechanism, let's say first come, first serve. If first packet 1 of A came, so it will transmit then. If packet 2 of A came, then it will transmit that. But then in between, packet 1 of B came, it will transmit that. Then again, packet 3 of A came. Then I have 4, 2, 3 of pink. Then again, let's say red, pink, red, pink, 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 and so on. So I would have sequence of packets from A and B not following a specific pattern. Depending upon queuing, depending upon when they came, first come, first serve, they would be transmitted across the link. They would have to wait in the buffer as well as denoted by the green box there. Packets are sent randomly. I need to transmit now. I'll start transmitting after a little while. Once my music file is transferred from A to C, I would stop. But B can continue transmitting. So I can have first red, pink, red, pink, red, pink, then only pink, 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 pink. Then again I start transmitting. I'll have again red, pink, and pink might stop. Then again red, 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 and so on. So this type of multiplexing is known as statistical multiplexing. I have written this. So we say packet switching employs statistical multiplexing, in which whenever you send the packet, you get the chance based on whenever the link is free. There is not a reserved guarantee of bandwidth. Okay? There is not reserved that you will get this speed at which the packet has been transmitted. There is no reserved guarantee that only these many delays, are suffered. So this is what basically we have as a packet switching network or packet switch network. So there are advantages, disadvantages of both, right? People would say that packet switching is not good in the sense that it's not good for a video call. It will deliver a video, but it will deliver a late one. It's like you're watching a cricket match. Okay. Ball has been delivered 5 minutes back and now you receive that. Okay, ball. So they say for real time services means telephone calls, audio, video, etc. It may not be suitable. But overall, in that case, they say, circuit switch networks would be better. But the advantages that we see in the packet switch networks are it's a better sharing of bandwidth. In, let's say, FDM, you have a frequency reserved for you. And if you're not sending anything, you're wasting that frequency. You didn't get the whole of it. And in this case, even if you have like time division, you are given a time slot. You do not use the time slot, you're wasting the time slot. Here you are giving, certain slot to transmit based on first come, first serve, let's say. So it would be better sharing of bandwidth and you can use the full resource that is available during that time. And if nobody else is using and you only want to transmit, you can transmit at the full rate. But there you will still have that 4 kbps. Here you can have 16 kbps. That means a full rate. Simpler. This is more efficient. This is less costlier than the circuit switch network. Clear? Okay. Any question? You can do a good comparison of this. I think I'll use some. Now we'll have packet forwarding networks also. I think we'll take that in the next class. It's already more than 1.5 hours, I believe, around 1.5 hours. So you might get bored after this. Do we have any question here regarding packet switching and circuit switching? No? All right, Ramanand, should we end the class then? All right, then we'll end the class. Okay, bye. Stay home. Be safe. Take care. Bye-bye.